In this video, we're going to talk about continuity at a point. So let's say we have a domain going from A to B, all right? A to B. And it's closed, by the way, at A and B. All the points, interior point between A and B, a function y equals f of x is continuous at an interior point C of its domain if only when this happens. Limit of f of x as x approaches C, that has to equal to f of C. And at the end point, which is at A and B, a function y equals f of x is continuous at a left endpoint A or is continuous at a right endpoint B of its domain if limit of f of x as you approach A from the right side is f of A, or limit of f of x as x approaches B from the left is f of B, respectively. So again, we're talking about continuity at a point, and we'll look at some examples. Let's take a look at this piecewise function from 0 to 4. So domain is 0 to 4. And basically, if you have a graph, if you're able to draw the graph without lifting your pencil, then you know that it's going to be continuous from left to right. So let's look at this function, y equals f of x. If you try to graph this function, right? So from 0 to 1, it's okay. But in order to get to this point, you have to lift up your pencil and start to draw over here. So you know that it's not continuous at x equals 1. Also, at 2, you got to draw open circle, and you have to lift up your pencil to draw that dot. So you know that it's not continuous at 2. And from 2 to 4, you are able to draw the line. So it's going to be continuous everywhere except when x equals 1 and x equals 2. That's using graph. What about using definition of continuity at a point? Again, we have a domain going from 0 to 4. It's closed at 0 and 4 because they have a closed dot right here. So let's check the endpoints. So what happens to limit of f of x as x approaches 0 from the right? Is that equal to f of 0? If this is true, then it's continuous at x equals 0. So what is the limit of f of x as you approach 0 from the right side? As you can see, it's 1. What is f of 0? What is the y value when x equals 0? It's 1. So we know that 0, the endpoint, the continuity at 0 is okay. What about f4? Limit as x approaches 4. Now you have to approach from the left of f of x. Is that going to be f of 4? Okay, what is f of 4? What is the y value when x equals 4? It's 1. And what is the limit as you approach 4 from the right side? You're getting very close to 1. So our endpoints are okay. What about the interior points from 0 to 4? Now the interior points are any number that are greater than 0 or less than 4. Any number between 0 and 4. So it looks like it will be continuous from 0 to 1, not including 1. And then from 1 to 2, and 2 to 4. I should put the union symbol right here. Okay. Now, what's happening at 1 and 2? It's not continuous because in order to be continuous at x equals 1, this has to happen. Limit as x approaches 1 of f of x. That should be equal to f of 1. What is f of 1? F of 1 is 1 because you have a closed dot right here. So f of 1 is 1. Now, what is the limit of f of x? You approach x approaches 1. Well, in order for this to exist, remember, limit of f of x as x approaches 1 from the left. That has to equal to limit of f of x as x approaches 1 from the right. As you approach 1 from the left, you're approaching 0. As you approach 1 from the right, you're approaching 1. These two values are not the same, so therefore limit of f of x as x approaches 1 does not exist. So that's why it's not continuous at x equals 1. What about at 2? Same thing. In order for to be continuous at 2, as limit of f of x as x approaches 2, that needs to be same as f of 2. What is f of 2? What's the y value? It's 2. Now what is the limit as x approaches 2? Well, as you approach 2 from the left, as you approach 2 from the left, the limit is 1. And what is the limit of f of x as you approach 2 from the right? As you approach 2 from the right, limit is also 1. You're getting very close to 1. So you do have a limit in this case, but it's 1. And 1 is not equal to 2. Therefore, it's not continuous at x equals 2. So again, when is this function continuous? From 0 to 4? It's continuous from 0 to 1, not including 1, and 1 to 2, and 2 to 4. Notice I have open parentheses because the function is discontinuous at x equals 1 and x equals 2. Let's go back to our step function or greatest integer function, y equals greatest integer of x. When you graph it, you get a step function. Now, let's see where this is continuous and discontinuous. It looks like in order to graph this, you need to lift up your pencil at every integer. So look, so you draw this line, you have open circle, and you have to lift up your pencil to draw this line over here at x equals -1. And you have to lift up your pencil at x equals 0 and draw the line. And you have to lift up your pencil at x equals 1 and so forth. So every integer looks like you have to lift up your pencil. So it's discontinuous at every integers. What about between integers? Let's say from 0 to 1 and 1 to 2, 2 to 3. Well, those interior points are continuous because you are able to draw the line. So therefore, based on the graph, this function is continuous from -2 to -1, -1 to 0, 0 and 1, and so forth. Notice I did not include the endpoint because at the endpoint, when n is an integer, as you can see from the graph, the function is discontinuous. So let's see what happens at 2.5. Limit of f of x as x approaches 2.5. Is that equal to f of 2.5? What is f of 2.5? Well, that's going to be 2. And what is the limit as x approaches 2.5 from left and from right? Well, that's 2. So as you can see, 2.5, which was between 2 and 3, is continuous. What about at 2? What is the limit of f of x as x approaches 2. Is that equal to f of 2? What is y value when x equals 2? Y value is 2. However, what is the limit as you approach 2 from the left? As you approach 2 from the left, it's 1. Or from the right, it's 2. So limit does not exist. Therefore, it's not continuous. How can something that doesn't exist equal to 2? Therefore, it's not continuous at 2. And you can make the same argument at x equals 3, 4, 5, at any integer. Now we're going to look at different types of discontinuity. Look at these two graphs. If you notice, there's an open circle at x equals 0. And here you have open circle, but there's also a closed circle when y is 2. These are the two types. These two graphs, we call it removable discontinuity. That's because for both of them, all you got to do is either draw a closed circle or move a closed circle to a different location to make it continuous. So these are examples of removable discontinuity. And notice, it's continuous everywhere except x equals 0. This one also is continuous everywhere except x equals 0. Now let's take a look at this graph. Again, this graph is continuous everywhere except x equals 0. Now, this is an example of jump discontinuity because in order to get from here to here, you have to jump to draw the line. So this is an example of a jump discontinuity. And this one right here is infinite discontinuity because as you approach 0 from the left, you go to positive infinity. And as you approach 0 from the right, you also go to positive infinity. So this function is continuous everywhere except when x equals 0. And notice this function right here, sine of 1 over x. As you approach 0, the limit goes between -1 and 1. Also, when you approach 0 from the right, the limit oscillates between -1 and 1. So this is an example of oscillating discontinuity as x approaches 0. But then again, this function is continuous everywhere except x equals 0. Now let's talk about intermediate value theorem for continuous functions. Sometimes we call this IVT. A function y equals f of x that is continuous on a closed interval a to b. So in other words, this function is continuous, meaning that you could draw the line without lifting your pencil. Takes on every value between f of a, which is the y value of a, and f of b, which is the y value of b. In other words, if y of 0 is between f of a and f of b, so you have y of 0, which is between the y values of a and y values of b, then if f of c equals y of 0, where c is the x value, for some c in between a and b. So in other words, if we know for sure that y of 0 is, if you got to first make sure that this function is continuous. If this function is continuous, and if there's a y of 0 between f of a and f of b, then there has to be a value of c such that f of c is y of 0, that c has to be between a and b. This theorem is useful because let's say we know that the f is continuous from 2 to 4. And we know that f of 2 is -5 and f of 4 is 3. That means there is 0. There is a 0, y of 0. Let's say it has to be 0 because 0 is between -5 and 3. So that means there's some c which is between 2 and 4 such that f of c has to be equal to 0, meaning that there's an x value such that the y value of f will be 0, meaning that there has to be zeros or roots of a function.